Good morning, good morning, good morning. How is everybody doing today? All right, we're back. And it is finally time for the postulates. Okay, so we've started postulates now. We've moved on from definitions. I'm going to let you go back. At this point, you might want to review the definitions by yourself. Remember, you can always check out the PowerPoint for them that we made as we made these videos. For the definitions. We're going to start on the postulates, and of course the first question for the postulates is, what is a postulate? Answer's pretty straightforward. A postulate is essentially something that Euclid says, I'm just going to assume this. I'm not going to try to prove it, and it's not a definition exactly. He's just saying, I'm just saying, let us assume that the following things are possible. And even though, while we had 23 definitions, we've only got 5 postulates. So there's only 5 things, and that Euclid is asking for is kind of a gimme. He says, let me just have these. Let me go ahead and steal my my Euclid art from my last from the last slideshow here. There we go. Put those in there. That makes it. I felt naked without them. All right, got Euclid back. That's Euclid. My face is probably covering him up a little bit. But here we go. Okay, so Euclid asks for 5 postulates. In order to do his geometry, there are 5 things he says we just need to let him have them. He can't prove them, and they're not definitions of words. He's not just telling us how he's going to be using his language. He's saying these are real ideas, and I can't prove it, but I just need you to give it to me. And if we can all agree that they're probably true, then we can do geometry together. After that, there's going to be common notions, but that'll be tomorrow. I'm hoping to get through all 5 postulates today. We'll see how it goes, but I'm really hoping we can do all 5. Whoops, that's not where I wanted to go. Here we go. So we need a new slide. Let's jump to postulate 1. All right, and I'm just going to actually leave it as 1 here because the postulate itself is pretty straightforward. That is, what Euclid says is, let it be postulated that we can. That it is possible to draw a straight line from any point to any point. All right? And this is, again, what Euclid is doing here. Let's put this in the center. That'll make more sense for these. Euclid is saying, look, I can't prove that it's possible to draw a straight line from any point anywhere in existence to any other point anywhere in existence. But I'm asking you to grant me that. I can't prove it. That doesn't mean I don't think it's true. In fact, I do think it's true. But I'm just going to say it. Right? Let's just assume that's possible. So we have to grant him that one. So we'll drop our, it's not technically a line, but we're going to pretend it's a line in here. And let's make it a straight line. And there it is. Boom. Right? So that's from this point to that point. If we wanted to make this really clear, and since I'm going to be stealing art from I'm going to be stealing materials from our definitions, let's go back to our definitions and let's find our point. Here's our point. We'll grab that. We'll drop it into postulates. And let's shrink it all together. Ooh, that did not work nicely, but we'll be all right. Fine. It'll be fine. We're just going to do that. All right, and now we're going to do that. Grab these, put these over here. Copy it. Drop those, put it there. And all right, so the point, you know where the points are. And let's go ahead and draw our straight line from point A. We'll call it point A. From point A here to point B. That is a straight line. It's on an incline, but it's still a straight line, and it's a straight line because all of the points on it are the same angle over the top or around the bottom to any of the other points on it. So that straight line, Euclid says, just give it to him that anytime you pick out 2 points, we're going to say it's possible to draw a straight line between them. All right, fair? I hope so. Move on. These should be fairly easy. It's not too hard, except for postulate 5. I'm just warning you, postulate 5 is a whole thing. All right. Number 2, the second thing Euclid needs us to just grant him, he says, just got to give me this one, is that it is possible to produce a finite straight line continuously. There we go. That's how you spell that word. In a straight line. Okay. This one's going to be, again, sort of hard to put on any actual, if we were using paper, it would be hard to put on paper. It would be hard to put on a screen. But all he's saying in here is that you can just make a straight line keep going for as long as you want. So let's go ahead and make a straight line. So if you take a straight line, boom. All he's saying here, so make sure I do this right. Snap into place for me there. All right. So there's our straight line. Let's make this a little bit thicker. All right. So there's our straight line. All right. So you've got a straight line, and he says it should be. He wants you to grant him that he can continue to produce it continuously. So you take a finite straight line, and you can continue to make it longer. So you can just essentially you can always make a line longer. So what I'm going to do is I'm going to add to our straight line starting at this point. I'm just going to keep it going. Since it's a continuation of the previous one, let's do that. And there we go. Oop, there we go. All right, so what he's saying here is if this is point A, we're going to start giving our points letters here. That's point A. And this here is point B. Right, that we can actually keep going through point B onto points C, D, E, F, and you can just always keep going, right? So that you can take any straight line and you can continue producing it as long as you like. That's postulate 2. So just that any straight line can continue to be extended in a straight line for as far as you want. All right, new postulate, postulate 3. He says he needs us to grant him, to allow the possibility, to allow that it's true, to agree with him that it is true, even though he can't prove it, that it is possible to describe a circle with any center and distance. And by distance, he seems to have basically meant radius here. Okay? And the word describe doesn't mean talk about for him. What he means is actually just that there can be a circle. So he says, let's assume that it's possible to create or to imagine or to talk about a circle with any center and any distance. So the center needs to be anywhere, and the distance needs to be as much or as big as or as little as you want. So we just going to start making circles here, right? So you can have, here's a way to do this right, but all right. So you can have that circle, and again, we don't believe in borders. There we go. And we'll have our circles be yellow because yellow is a pretty color. All right, and so you can have that circle, but you can also have that circle, and you can also have an even bigger circle. A really big circle. Let's move our circles here and send this to the back. All right, so you can have any circle, a circle with any, you can have a circle with its center anywhere and its distance as big as you want. So let's assume that in order to do geometry. So far, these are fairly uncomplicated things, and people generally have been pretty happy to grant them to Euclid. They say, okay, Euclid, you can do that. But if you have any problem with any of these postulates, feel free to leave me a thing in comments. Let me know why you're not so sure that we should just let him just have that. That you think maybe that needs to be proved that it's possible to do that thing. Okay, postulate number 4 is that all right angles. I like this one, by the way. Angles are equal to one another. He can't prove this, and this is maybe the first one that it maybe starts to bug people a little bit, because that feels like you ought to be able to prove it, that all right angles are equal to all other right angles. And Euclid's like, well, I wish I could, but in fact, I can't prove that. I do definitely think it's true. I'm sorry, I'm scrolling here because I'm looking for my right angles here. Here's my right angles definition. Here are my right angles, right? So there are my right angles. I'm going to steal them for this other PowerPoint. There we go. Right. So let's just do some other ones over here. I'll do a third set down here. Right. So you got angle. So since they're right angles, we know that angle A is equal to angle B. Let's see if I can get that in here. Angle A is equal to angle B. All right. So we know that, and that's what makes them right angles, because angle A is equal to angle B, and these lines are perpendicular. But that also means that according to Euclid, let's put some values in here, new angle numbers, angle letters. There you So if angle B is equal to angle A, then Euclid says you also have to grant him that that means that that angle C is equal to angle D, and that angle E is equal to angle F, is equal to angle F. But not only that, but also that all of these are equal to each other, right? So angle A equals angle B, and also equals angles C, which equal angle D, which equal equal angles E and F, even though they're not on the same line. In fact, they're entirely different from each other, right? So what this bit right here, this is what Euclid is trying to say with postulate 4. He says, you just need to grant me that if A and B and C and D and E and F are all right angles, then they're all equal to each other. Okay, that does actually seem very reasonable. It seems intuitively makes sense to me that they would all be. But again, notice that Euclid is saying he can't actually prove it. He's pretty sure, and he needs you to grant it to him. With all of that said, here we go. Here comes postulate 5. And we need a new slide for postulate 5. Nope, that's not where I want to be. I want to be here. Let's center that sucker. 5. Postulate 5. All right. And there's more typing in postulate 5. There's more words in postulate 5 because, again, this is the big one, folks. That if a straight line falling on two straight lines make the interior angles on the same side less than two right angles. And this is seeming complicated, but I promise we'll break it down. Two right angles. The two straight lines, if produced indefinitely, meet on that side on which are, oops, I didn't write that one. On that side on which are the angles less than the two right angles. And angles got spelled wrong incorrectly there. All right. What on earth is Euclid saying here? Well, this is generally he's talking about parallel lines, the short version of this. But let's break this down a little bit more. Okay. So he says if a straight line falling on two straight lines make the interior angles on the same side less than two right angles. What is he saying there? Well, let's do it, and I'll show you what he's saying there. So here is a straight line, right? And here, let's just do that a little bit. And okay. And just copy it. Make a new one here. Here's another straight line. Right? And here's a third straight line. Okay. So here we have a straight line falling on two straight lines. Let's just make this a little easier. I'm going to do this, right? A straight line falling on two straight lines make the interior angles on the same side less than two right angles. The two straight lines, if produced indefinitely, meet on the side on which the angles, which are the angles less than two right angles. So what does that mean? Well, okay. Let's make this a little bit more extreme to make this easier for you to see what he's talking about, at least. All right. Do that. All right. So what you can see is you've got one straight line falling on two straight lines. That's sort of what we're kind of used to that. And we notice that we are not dealing with right angles here because this angle is, let's go ahead and put one of our little angle doohickeys in here. We need to start labeling our angles again. So let's go ahead and put an angle circle in. All right, there we go. And no fill. We want our outline. I use a standard. Okay, there we go. Okay. Let's put another one. I'll just copy that one and put it over here. Okay. All right. And now I'm going to start to steal one of these. Not going to do that. B. But this can't be angle B as well. It has to be angle A. Let's go ahead and label all of our angles just to make all this entirely clear to everyone. Even though it's going to take a minute, just sort of need you to trust me that the time it takes is worth it. C, D, E, F, G, and H. Okay, there we go. And let's actually, you know what? Let's label these lines too. So let's say this is, we'll call this one line Z. We're going to call this one line Y. We're going to call this one line X. Okay, there we go. Now, I think now we can do this. Okay, so we're following Euclid. And according to Euclid now, it says if a straight line falling on two straight lines, make the, okay, so far so good. We did that. We have one straight line falling on two straight lines. Make the interior angles on the same side less than two right angles. So we know that H is less than a right angle and A is less than a right angle. So they are the interior angles. They're not on the outside, but they're on the inside. They're interior angles on the same side of X, right? So that means H and A. So if, let's go ahead and drop in another word box here so I can sort of understand this. Okay. So if angle H and angle A are less than right angles, and we know that they are on the same side, are less than two right angles, the two straight lines, that would be Z and Y, if produced indefinitely, that means if produced forever, meet on that side on which are the angle less than the two right angles. That is to say, they meet on this side. They do not meet necessarily on this side. So he's just saying that at some point, if we were to draw these angles, these lines out forever, remember, indefinitely just means without ending, right? If we were to draw these out forever, these two lines would meet. So let's just check and see what he's saying here. So let's go ahead and drop in our gray this line continues line. So continue that one that way. And if the other one goes here and connects to the end of this line and continues in the direction it's going. There we go. Oh, that didn't work. There we go. Look, they do in fact meet at, point M. Doesn't matter what we call it, but point M. So they do meet. That, he's just saying let's assume that they will, because it's not always clear that will happen so easily. So for instance, if we were to do this, if this looked a little bit more like this, and this looked a little bit more like, bring this down a little bit more, that up a little bit more, right? And let's just keep going line Y can really make this tough. All right, so here you can see, like, yeah, you can kind of tell that they're probably going to meet at some point. This one is sort of here-ish. Right? You can tell that they're probably going to meet at some point. You can't see where they meet, but you can tell that they kind of probably will meet at some point. In fact, it seems sort of obvious to us. We tend to assume that this is true. We've always assumed that this is true. In fact, or at least we being kind of people, have almost always assumed this is true. And people actually are irritated. When people get irritated about postulate 5, what they're irritated about mostly is the fact that it is a postulate, that Euclid didn't feel like he could prove it. And in fact, for years and years, and I'm going to post these videos and actually ask you to watch them tomorrow, people have been working on trying to prove postulate 5. Take it from being a postulate into actually being a theorem. We're going to get to his actual, his proofs, and Euclid's proofs are the fun part. That's where things are really going to get exciting. But people have assumed forever, or at least hoped forever, that they could find a way to prove postulate 5, and they've never actually been able to do it, which is a bit of a spoiler there. So Euclid's going to say, no, I can't prove this. It seems like it should be true, right? I mean, the really short way of saying this, by the way, is what Euclid has in postulate 5 is saying parallel lines never meet. Euclid says we have to assume parallel lines never meet. He says, I can't prove it. And that, I'm kind of curious if it frustrates you, but I will let you know it has frustrated mathematicians and geometricians for ever since there's been Euclid, ever since Euclid. So a very, very long time. All right, that's all we have for today. If you are also frustrated that postulate 5 has to be a postulate, go ahead and leave me a comment about it, and maybe we can talk about it some.